Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. We got a weird one for you today. In our last video, we talked about how to do dot products. Dot products is one of the ways that you multiply two vectors together. And dot products are really interesting and kind of weird in that when you multiply two vectors together with a dot product, the result is not a vector. It's a scalar number, just a single number. We talked a lot about how that number is, in some senses, a vague representation of the same directionness of the two vectors that you're multiplying with the dot product, and that was very fun. Before we can get to do really cool calculus on vectors, we also need to know about the other kind of way you can multiply two vectors. And the other way you multiply two vectors is called a cross product. And again, they're named like this because one of them uses the dot symbol, one of them uses the X symbol. In normal multiplication, these mean the same thing. If you're just dealing with numbers, they both mean multiplication. In vector world, these mean two completely different kinds of multiplication that have nothing to do with each other. There's no relationship between these two things at all. Dot products sort of make a certain amount of sense. You can kind of see, if you play with enough examples, you can see that the result of the dot product does sort of correlate with the same directionness of two vectors. Cross products, I don't think they make a ton of sense. Maybe they do and I just don't understand them. But anyways, I don't have any sort of clever build-up to this. I'm just going to tell you how to do a cross product, and then we can do some examples, and we'll talk about what the cross product means. Cross products, the first thing we need to know about cross products is that cross products only work on three-dimensional vectors. So if you have a vector u, it has to be three-dimensional. Let's say u is 1, 4, negative 2. And let's say we have a vector v that is 5, 0, 8. These are two three-dimensional vectors. One of them points right and up and back, I guess. One of them is kind of pointing in that direction. One of them points left and out. One of them is pointing like straight in this direction without going up at all. The cross product of these two vectors in 3 space, one of them goes this way, one of them, let me see if I can do this with 2 markers. One of them is going back this way, one of them is going straight this way. The cross product of these two vectors will be a third vector, and that third vector will be perpendicular to both of them. Which is kind of cool. If you ever need to get something that is definitely perpendicular to two other things that are just sort of pointing in weird directions in 3 space, the cross product will give you that third vector that is perpendicular to the first two, no matter where the first two are. It's interesting to note that there are, in fact, 2 different directions that this third cross product vector could go. If these are our two vectors, one of them pointing that way, one of them pointing that way, something that points sort of up and out is one way to get a vector that's perpendicular to these two. Maybe this is too far away. We'll get a little closer to the camera. This red that's going up and out is one way to do it. We could also get something that's going in the exact opposite direction, down. So the difference between whether you're going to get the red vector as a cross product of the two black ones or the green vector as a cross product of the two black ones, that difference comes from which order you put these in. And the general rule of thumb is if you position your right hand, here's my right hand, if you position your right hand so that it's going, so that your fingers are kind of curling from the first vector into the second vector, the cross product will point in the direction of your thumb. That's called the right hand rule. If you curl your fingers from the first to the second, you'll get your thumb will point in the cross product vector. So if this, that's the red one is what we get if this one's first. This one is V. This one is U. So if V crossed with U should give us this red vector that points up. U crossed with V, we go from U to V, we should be getting the green vector that points down. Let's test this out and actually learn how to do a cross product. The mathematics of actually calculating a cross product are kind of a mess, so bear with me here. When you're doing a cross product, let's do U cross V first. When you're doing a cross product, the first thing you need to do is construct a 3 by 3 matrix. The top row of the matrix is always ijk. The second row of the matrix is always the vector u. And the third row of the matrix is always the second vector here. The cross product of u times v is the determinant of this matrix. Determinant is something that we haven't talked about before. Determinant is an operation you can do on a matrix that will, in linear algebra, it tells you some interesting information about matrices. It's pretty important, especially for finding matrix inverses. But we're not doing matrix inverses here. All we want is the actual cross product. And we can get that here by finding the determinant. And the determinant basically means we're going to expand across the top row. And expanding across this top row means you take this first thing, the I. Pretend that the row and column that contains I don't actually exist. So when you're doing the I piece, all you're looking at is the 4, the 2, the 0, and the 8. So it's I times, what you do is you multiply these things across and then subtract them. So this will be I times 4 times 8 minus negative 2 times 0. That's the first piece. The second piece is, and that's from this little 2 by 2 matrix that excludes i's row and column. The second piece is minus j. So when we're doing the j, first of all, it becomes negative. The middle one always goes negative when you expand things like this. So j gets negative, and then we're going to pretend like j's row and column don't exist. So when we do the j piece, we're only going to look at the 1, the 8, the negative 2, and the 5. And we'll do the same thing. 1 times 8, do that multiplication minus this multiplication. Minus negative 2 times 5. And then for k, we do something similar. For k, we go back to plus. So I is positive, j is negative, k is positive when we do a cross product like this. The reasons for that come from the nature of taking the determinant of a matrix like this and the rules of finding the determinant. I could probably talk for 40 minutes about finding determinants very easily, but you don't actually need any of that context or information for this. We just need to know how to do the determinant of this particular 3 by 3 matrix for a cross product. So I'm not going to spend a ton of time on determinants. Trust me that I is positive, j is negative, k is positive again, and we're going to ignore this row and column. And k, we're going to multiply 1 times 0 minus 4 times 5. And then you just calculate these things. 4 times 8 is 32 minus this is 0. So you should get 32i. This is 8 plus 10. but it's negative. So negative 18j. And this is 0 minus 20, so minus 20k. So this is a vector that is going that way and down and back. So this is the green vector that we said. This one is u pointing mostly up and back. That 4 and the negative 2 is up and then back. And this is v pointing right and out. Then this green vector is pointing right and down and back. Hopefully you can see angles in this camera. I don't know how else to do this. Right and down and back. It's going that way. Which is exactly what we thought. That's what the right-hand rule is supposed to tell us. So, I promised that this vector, and it doesn't have to be vertical. I'm only writing this vertically because I was going to run out of room horizontally. Probably best to write this as 32i minus 18j minus 20k. Probably best to write it like that. I promised that this vector would be perpendicular to both of these. And the exciting news is we can verify that because we know how to do a dot product. Dot products give us a measure of the same directionness of two vectors. And dot products are always 0 when two vectors are perpendicular or orthogonal. Orthogonal is a fancy word for perpendicular that sort of only applies to vectors. Or I guess it applies to anything, but it's used more often with vectors. So we can check to make sure that these vectors are actually perpendicular. I need a name for this. I'm going to call this, I'll call it C for cross product. So I can find C dot U. If these are in fact perpendicular, then this should be 0. And we can calculate that. C dot U is going to be 32 plus negative, what was that, 8 less than 80, 72? 32 minus 72 plus 40? Bam, perfect. It's exactly 0. This thing is perpendicular to U. Let's see if it's perpendicular to V. C dot V should be 160 plus 0 minus 160. Beautiful, perfect. This is a really easy way to check your answer. If you're doing cross products on a test or a quiz and you're not sure if you've done them correctly, just take the dot product of the component pieces. If you did your cross product correctly, your dot products, both of your dot products will be 0. Because the correct cross product is definitely going to be perpendicular to those things. Couple other quick notes on cross products. The idea of creating a 3-dimensional vector is why these cross products only work in 3 dimensions. You cannot take the cross product of 2-dimensional vectors. You would end up with a non-square matrix, basically. Because you need to have one row as a vector, and you need to have this row as a vector. And so 2 of your rows need to be vectors, and the 3rd row needs to be i's, j's, and k's. And so the only way to get a square matrix out of this is to do this exclusively with 3-dimensional vectors. It only works when your vectors have 3 components. You can't do it with 2 components because then you don't get a square. You can't do it with 4 components because then you still don't get a square. Maybe you'd have to like add a 3rd. I don't know. It's probably not going to work. Cross products only functionally work for three-dimensional vectors. The last thing that I want to say about them is overwhelmingly the thing that we're going to do with cross products is we're going to use them to find vectors that are always perpendicular to something. So it won't come up immediately, but towards the end of the class we're going to be looking at vector fields that represent a surface, and we're going to want to find things that are perpendicular to that surface. So we're going to be using cross products to find vectors that are always perpendicular to three-dimensional surfaces, and we're going to use those in integrals. So it's going to get pretty intense. Stay tuned for that, but it won't happen for a little while. We have a couple months before we start getting into that stuff. We just need to have this sort of foundation for cross products ready to go for when we get there. The last thing I want to say about cross products in this video, and I'll make another quick one where I just do a couple more examples, because the math here is weird, and like just one example is not enough. So stay tuned for that. But before we do the second examples video, the last thing I want to say about these is that there is one other sort of utility for cross products. Again, the important thing is you get a vector that's perpendicular to the two inputs. The other important part about this is the magnitude of this vector is equal to the area of the parallelogram formed by these vectors. So if you think about these vectors being up and back, and this one being sort of straight over, these vectors form a parallelogram. If you put a copy, this is U, this is a copy of U, this is V, this is a copy of V. Any two vectors in 3 space can form a parallelogram. And the area of this parallelogram is the magnitude of the cross product. I don't think that's ever going to be super relevant for the rest of Calc 3, but it's handy to know, and I'm pretty sure it comes up at least once in this homework assignment. So, now you know, and knowing is half the battle. That's it for this video. Stay tuned for a couple more examples of cross products.